Hello everyone, good evening. So we will start the third session of this reinforcement learning TA session for nptel, and hope your courses means this course is going well. You are understanding. Any issue till now? Hello. Any issues you're facing? No issues. Thanks. Okay, maybe wait a little bit more, or maybe we can start as well. Okay, we will solve these problems that I have listed here today, and see if you can understand, ask any doubts if there is. Okay. Uh, which of the following statements for epsilon greedy approach? Okay, which are the correct statements? Okay. Always keeping this epsilon as constant is a good idea, or and other options you can see, large value of epsilon will lead to unnecessary exploration in the long run, and cooling down epsilon too fast is problematic as it cannot guarantee correctness in value estimates. So what do you think here? What should be the correct option here? Epsilon greedy was approach was covered in the week one. This question from that. Okay, option D. Uh, so what permissions I have here? Okay. Option D is the correct one. Yes. So keeping epsilon as constant is not a good approach, because our approach should be that we keep a fixed value of epsilon for some time and keep the exploration on, then reduce the epsilon and then continue doing that and repeat after that. Okay. So why is this important? Because uh, this epsilon denotes the randomness in our prediction. So we have to approach in such a way that the randomness reduces as we progress and we get to a better estimation. Okay, so that is why option 1 is false. Okay. Okay, and as you know, for any um, we do uniform exploration for any banded arm, and using the probability this. Okay, n is the number of banded arms. Okay, so if the epsilon is large, that will lead to large number of explorations. Okay, and cooling down epsilon too fast is problematic as it cannot guarantee correctness in value estimates. Yes. So what happens if you are cooling down epsilon very fast? What happens that you are not exploring enough. Okay, so estimates will be poor and noisy, means like you are getting too fast towards exploitation. You understand? So that is why it is not a good idea to move very fast towards exploitation, because you need to have a better estimates. So that is why the epsilon should not fall too fast. Okay, falling is important as we have denoted here, but it should not be too fast. Okay, so this is our question on epsilon greedy approach. Correctly summarizes the situation, and just to give you that, the probability of having this action A, just to for the sake of completeness, you already know these things, I know, but for the sake of completeness, to list out down the formula. So probability of occurrence of this action A is this. So this is the exploitation part probability, and this is the exploration one from this. Okay, and with this probability, we with now with this exploitation probability, we are choosing this argmax A. We're maximizing because it is a greedy approach, so we need to take the maximum reward. Okay, so but the previous greedy approach did not work. Why? Because if taking the maximum, like in the class also you'll have example. So these are the bandits. Suppose at first instant this gives the maximum, that is 1, and others are 0. Okay, but so consequently in the next step also I should take this one, but the situation might have changed, that this is 1, this is 50, and this is 0, this is 2. In this situation you should take this one. Okay, so the purely greedy approach does not work well. Okay, so this epsilon greedy approach. Okay, so clear? Clear everyone? Any doubt? Something? Yes sir, clear. So epsilon greedy, and the greedy approach, that is the pure greedy approach, is just the uh, previous of that, that is that you just take maximum of that, but you may end up with wrong solution actually with that. Another is the softmax one, in which you will not explore every solution, but you will explore the one with the maximum probability, and keep doing that. Okay, with the maximum softmax probability. Okay, so that is it. So let's continue. Okay, so this is a
Sir, for
question.
the previous question answer, sir.
Acha, answer is this one. Yes, 2 and 3 are the correct one.
Okay, sir.
First option is wrong, as keeping it is constant, the our randomness does not reduce. It is still if epsilon is 0.1, so the 10% of randomness persists towards the end, even at the end. That is not desired. We need to reduce with time and get to a better estimate. Okay, so the pack optimality question. So just to illustrate, the pack optimality was this one. So this epsilon and delta, these are the two parameters we have. So what you're trying to see is this probability q star a is greater than equals to q star a star minus epsilon is greater than equals to 1 minus delta. Okay, so this is the situation. Okay, so what we're trying to what we interpret from this, that we are trying to estimate that the probability uh, that our arm A, okay, or our action A, okay, and the q star is the uh, estimate of the reward, right? So that is greater than or equal to, means that it is less it is greater than the, and this q star A star is the or optimal estimation of the reward. Okay, so it is little less than that. Okay, so and in the bound epsilon, okay, means like it is between plus minus epsilon of this one. Okay, so like that. Okay, and so that is greater than this probability is the delta will be also small. Okay, so that it is a high enough value close to 1. Okay, so that is the probability. So we are trying to uh, get to this estimate. Okay, so that is the pack optimality situation. Okay, so we are given a delta and epsilon. We're trying to minimize the step to reach to pack optimality. So we're trying to reduce the number of steps n here to get to this estimate. Okay, so that is the idea of the pack optimality. Other than this are not correct. Okay, uh, so it is the theory actually, so not much like a multiple choice question, not possible to explain the other one. Del and n given a n is not possible, n is not known. Now how many steps will be required for optimality is not known. Okay, so these two options are gone, and none of these is not correct because we have already got one option. Okay, any doubt? All clear? You're able to understand well the course? Okay, Himanshu. Okay, so let's progress towards the next question. So the credit assignment problem is an issue assigning a correct mapping of reward accumulated by the action. Which of the following is the reasons for the? So so you're trying to assign a reward. Okay, credit it is called here. Okay, so the reward may only be observed after many time steps. Actually, reward may not be immediate. Okay, so it's not an immediate RL situation. This is correct. Okay, there are other also RL. Okay, which will not give you a reward immediately. Okay, okay. So so this one is correct. Okay, and so may get same reward for multiple actions. Okay, uh, so let's think about that. Credit assignment problem. A little bit description on the problem can be good. So as you can see, there is a delay between the action and feedback received. Okay, that is the simple one. Okay. So the reward signal is received only at the end in this problem. Okay. And okay. Same reward for multiple actions. The agent discount rewards the occurred in the. I don't think there is relation between the previous steps actually. So this one is incorrect. Reward can be positive or negative. Can they be? Uh, Sign credit. Okay. So credit is most probably positive here. Not sure actually. The diagram. So here it is negative. Negative is possible, I guess. Okay. So it can be positive or negative. Okay. An agent may get the same reward for multiple actions. Mm, it is possible, I think. I think this is it really. Same reward for multiple action. Same reward or different reward, that is not written anywhere. This type of problem. Mm, in general, it can receive, but like in this problem, I'm not too sure. Anybody has done this question? Hello? Not sure about B option actually. In general, it should be true, but don't know for sure. First option is the best option overall, but D can also be, because it is a situation reward accumulated by actions, because it's accumulating over time, over steps. So the most appropriate option is A. So I think maybe this is the only option, or maybe some other also there, because all that applies written. Hmm. This is the question. Little bit confusing. Anybody has done it? What is the solution here? Or solution is given. Little bit of interaction. Yes, it is multiple options are correct type of question. The most relevant one is this one, okay? But I think B and D can also be answered. Credit assignment problem, the main context is that it is not an immediate RL problem. So that is why this is the answer, okay? But okay, don't need to waste too much time over a simple question. In stationary bandit problem, we achieve asymptotically correct behavior by selecting exploratory action with a fixed non-zero probability without decaying exploration. So the thing is that in stationary bandit problem, the The stationary situation is this, that you have a probability distribution from where you are sampling the rewards. So this is the axis denoting rewards, okay, for different arms, okay. um, okay, and this is the probability with which you will get it. So these are the axes, okay. So this from stationary you are so the distribution is stationary, the parameters of the distribution or the distribution as a whole is will not change with time, okay. So this is the thing, okay. In non-stationary bandit problem, the reward distribution is not stationary, means the reward changes with time, okay. Means like, okay, the parameters of the distribution itself can change, okay. The type of distribution can change, okay. So many things can happen, the distribution does not remain same with time as the as our exploration is continuing, okay. So that is the difference between stationary and non-stationary problems, okay. Now the thing is that in stationary problem, the probability, so you can see this is written non-zero fixed probability, okay. So so the situation is like uh, so let me write it down. So in the non-stationary problem, so we get to the estimate of the reward for a specific action A at time t using the equation, this equation, okay. This is q, okay. Qt minus 1 k, okay. So so this is the situation. So we are decaying the probability of the previous estimates, okay. So as time progress, the not just previous, means every estimates that we're getting, we are decaying hyperbolically, as in the previous situation, previous session we have explored. Hyperbolically we are decaying the probability of occurrence uh, of a what do you call that, action, okay. Okay, so the probability actually decays to 0 here, okay. So why this is not correct? Because non-zero is written, okay. In this situation the probability decays to 0, means like at when you take so many samples, okay, uh, of this reward, okay, many times, so the estimation becomes a deterministic situation, not a probabilistic, okay. You can deterministically say whether this actually will happen or not, okay. So that is the idea in stationary bandits. But in non-stationary bandits, the situation is that probability of exploration goes to 0, okay. It cannot go to 0 because at every step you have to estimate the, because the distribution is changing, okay. The probability that our this action is the correct one, okay, that should not go to 0, because we have to always account for how the distribution change, and accordingly we have to change the probability, okay, and take the action with the maximum reward estimation, okay. So that is why these both are false, okay. This should be 0, this is non-zero, okay, but they have written opposite, okay. That is why this is the answer, okay. in in non-stationary problem, this decaying factor is 0.1 or 0.2, anything less than 1, okay. So you're giving more importance to the current estimation, okay, so that you get a better estimate with higher probability for that action. Okay, understood? Any doubt,
Yes,
let
sir.
me ask me. Okay, okay, yes. Any doubt? Okay, doubt, I think. See, no doubts. Okay, just let me take a call now. Okay. হ্যালো মা, ক্লাস চলছে, খুব ভালো চলছে আজকে, ক্লাস চলছে, পড়াচ্ছি। ঠিক আছে, রাখছি। Okay, so let's continue on to the next problem. So this is a very simple problem, but if without the graph this would have been a difficult one, maybe difficult one, but still not. Plot the functions they have told, but they have plotted it themselves. Okay, so least regret is the area. Regret is the area in this curve. Okay, so this yellow function has the least regret because it has minimum area under the, and not under the curve, you can say above the curve. So this is the situation. So this one is this. This is the correct answer. Okay. What are the properties of a solution method that is pack optimal? Okay. Okay. So let us see this problem. Okay. It is guaranteed to find correct solution. It minimizes sample complexity to make pack guarantee. Okay. Okay. So properties of a solution that is pack optimal. It is guaranteed to find the correct solution. Kind of yes, because like uh, what is the situation that can go wrong? Let's see the pack optimal things I've written. This is the one. No, pack optimality. This is the one. Okay. So is it guaranteed to reach a solution? But given these parameters, actually, you choose the wrong parameters. May not be guaranteed. Uh, mm, Depends on the parameters, actually. Vary the parameters properly, then we can get to the solution. B is correct.
Sir,
Okay. Say.
sir, can you show sixth slide, sir?
Okay. So this is the one. 1 minus 2 to the power minus t.
Okay, sir.
Okay. So it minimizes sample complexity to make the pack guarantees, because it is exploring such uh, this actions which are guaranteed by this expression. So it is reducing the number of samples to explore. Okay, so B is correct, that's for sure. Okay, it always reaches optimal behavior faster than an algorithm that is simply asymptotically correct. Yes, it is correct. Okay, so in that way B and C, I think B is the answer. But it is guaranteed to find the correct solution. May not be guaranteed, yes, the parameters are need to be correctly tuned actually. So that is why this answer. And the C part is correct. This reaches optimal behavior faster because it is not exploring every action here. Only the given, only those who are satisfied by the inequality, this inequality, this inequality. Okay, okay. So B is the answer. Means both B and C. Any doubt? Any doubt? Achha. So the pack expression is already written in the previous slide, so I have not written it again. Any doubt? No doubt, right? So these questions are from the previously run nptel this course only, but previous year it was happened. So these are you can say PYQs, previous year questions, just to learn better. Okay. Okay. So this is the question. Okay. Um, so first option is wrong. Okay. This is only possible in immediate RL. This is not immediate RL situation. Okay. It may not be immediate RL situation. So for every action there may not be reward. Okay. For the last action there can be reward, or after some collection of actions there can be reward. Okay. This is not necessarily correct. Okay. So acha, so not correct. Okay. So yes. Okay. Reinforcement learning is neither supervised nor unsupervised. So this is the correct one. Okay. Two reinforcement learning agents cannot playing against each other, cannot learn playing. So it is possible. Okay. So they can play against each other, and the end result, suppose they're playing a game of chess. Okay. So at the end someone wins. Okay. So they get a reward, and another one who loses get a means reward in the anti reward, you can say. Okay. So that way they can learn. Okay, amongst each other. Always selecting the action with maximum reward will automatically maximize the probability of winning a game. So this is the maximum. This is the greedy approach. Okay, raw greedy approach of which is focused on exploitation only, not exploration. So that is why it does not learn to explore well, okay, and the estimations are poor and noisy, okay. So this is not correct. It will not maximize in most situation, okay. The pure greedy approach does not work, okay. So this is the wrong one. Actually, cannot. This is also wrong one. So only one correct, okay. So this is 2, okay. Correct, okay. Understood. Understood. Okay, yes sir. Okay, so let's continue. Taking exploratory action is important for RL agents. That is correct. Okay, and what is the reason? To get a better uh, estimate of the reward while exploitation. Okay, so reason is not correct. If the reward obtained for actions is stochastic, an action which gives a higher one, it may not give a. So that is not correct. Okay, so exploration is important to get a better estimate. Okay, but it is important even in uh, when the stochasticity is not there, means the rewards are deterministic, but then also you need to exploration is still important, okay, to get a better estimate of what reward should be given while exploitation, okay. So this one is not correct, okay. So even in non-stochastic situation, deterministic situation, this is important, okay. So answer is the assertion is true and reason is false. Okay, any doubt or more explanation required here? Any doubt? No doubts. Okay. So this is the previous question only with more options. That's it. Because it is a better constructed question. Because the previous question we did previous week, it was just none of these as the answer. But why it is uh, so better choice as requires less complex computation. So that's not correct. Okay, simple reasons like you can use a calculator and computer. So complex computation is usually never a problem. It is better choice that it can deal with negative values of. So this is the answer actually. Uh, this probability will come negative then in this situation if the qt is negative, but in this situation it can never be negative, so probability is always positive, positive or greater than 0 or equal to 0. That is the definition of probability. Okay, it has to be greater than equal to 0. So this is the one. Okay, both are not good. Okay, because the second reason it is uh, it may not actually means like higher values both can be higher actually, okay, so it may not be able to differentiate very well. Acha, okay, wait, what did I say? So Okay, 1 is better because it can differentiate between close values of qt. Difference will be more on the exponential one actually, yes. Okay, so in the exponential one, so just to give you an example, uh, suppose we take e to the power 10, say 100, okay, and 100 means we need to differentiate between 100 and 100.1. Okay, so if we go by the exponential means Maclaurin expansion, so this will be okay okay, to the power x. Acha. Acha. So so let's interpret it like this, okay, that this is, if you take 100 common from here, okay, e to the power 100 common from here, what we'll get is it is hard to explain, e to the power 0.1, right? And this e to the power 0.1 value is significantly higher than 0.1. So is the, you can understand that if you're comparing 100 and 100.1, so the difference is to compare them is 0.1, which is okay, but this one is larger, okay, so that it is easier to differentiate in the case of this one, okay. So this large value you can see, uh, okay, so lot larger, okay, so it is easier to differentiate in the case of exponential, okay, compared to this linear ratios, okay. So answer is this is not correct, this is the correct option, second option, okay. Clear, right? Wouldn't second be closer? Second means which second to do, mean second option in this, or second this one, and close, what do you mean by close actually? If you can unmute, writing this much will be very hard. Second be closer. Closer, I mean, the okay, let me explain again. So that when I'm comparing, so what I need to do is I need to compare between these two, okay. So the difference, difference, the comparison, the point of comparison is the difference here, which is this, and in this case the difference is e to the power 100 times, okay, and so when I'm taking, so I can take this common, okay, acha, so this one is also there, yeah, acha acha, oh, if less than one, then it goes to less. This is not a high value, right? While taking the difference, we are taking this common. This one is clearly higher. Acha, this is 1.1 something, 1.105. So this is 0.105. Okay. Again, you can see this multiplying by these two. That was incorrect. Yes. But you can see this is 0.1, the point of difference. Okay. This is 0.105 multiplied e to the power 100, which will be quite a substantial value here. So you can see, may not be possible to calculate here, I don't know. E to the power 100 is a large value. Acha, this has to be one less, right? Okay, what do I do? Okay, first minus 1 here, okay, and multiplied by e to the power 100. This is okay, huge value, you can see. Okay, understood now. My statement still stands, okay. Just the previous calculation and interpretation was wrong, okay, but you understand, right? Multiplied by e to the power 100 is also there, okay, so it is larger, okay. So in the proof of the UCB algorithm, where when L is equals to this, you can see. So the point was in this derivation, you can remember that. So if you explain properly, so in the proof there were three situations, okay, that q a star, okay, is less than equals to q star a star minus c m t a star s, okay. So so what we are doing is that we are underestimating the our true estimate, okay, and to get this estimate, okay, and by what value? By this value, okay. So this is the our confidence, okay, in this case, okay. So confidence of underestimating here, underestimating the true value here, okay. So what does it mean actually? So so it means that suppose you're given this two q values, q a, q b, okay, and this is our confidence interval, okay. So what am I doing is that when while looking at only this one, okay, what I am doing is that I am taking this value which is like the bottom one, okay, compared to the true estimate. The true estimates lies in this middle, okay, and this is in the bottom. So that is the estimate we are taking. So this is one situation, okay, and derivation you can see this three situations are there. Another is this qi is larger than, so so what does I represent here? So I is this another one, okay. This is a, this is I, okay. So written b here, so correct this one. This is I, okay. One is a, another is I, okay. So what we're doing is that we're overestimating this one, okay. So suppose estimating here, okay. So so this is the another situation, okay. C M T I S I, okay. So these are the in subscript actually, okay. C is the bigger one, okay. So this is the another, and the margin of estimation or the confidence interval is this one defined by this. Okay, so that is another one. And the last situation is that this q star a star. So these are the problems that can happen, okay, while estimating q star I plus 2m okay. So what does it mean, is that okay, so so the situation is this, okay, so this is our old, okay, so it stands in the middle, okay, so we get a new one, suppose here, okay, and the new one for this one is here, okay, and so what it says that this one, okay, wrongly may be interpreted as greater than this one by how much margin? This two added together, okay. Okay, so this is the situation, okay. So the point is that as the number of samples that we take becomes more and more, this estimation error will this wouldn't go to this will non-existent or go to zero, okay. So this problem will not happen. So the point is that, okay, so from that we get to this point is that well, L is equals to this, okay. So at this situation this uh, uh, so this we are exploring the last scenario, last inequality. So when L is equals to this and this is equals to this, okay, which of the following correctly explains, means you get to a situation when these are equal, okay, the inequality doesn't hold, okay, which of the following correctly explains this being less than 0 when we replace this fixed value of L by the TISI. Okay. Okay, so what we are doing here is that so this is our one expression here, this is our previous expression here, okay. So we have got this one from this, okay, using a substitution, that is this one, okay, CML is equals to this, and del I, what do we get from that? Okay, let me see. So this t value represents the time at which we have sampled. Okay, so ith sample si we are taking. Okay, so t is that value. Okay, capital T, and L is the number of samples that are already taken. Okay, number of times the action has already occurred. Okay, so what we are trying to see here, these options you can see, this TISI, the number of actions to be taken, is the expressions. Okay, LM is what? M is here, I think subsequent actions. So I think that C, when second option will not be the correct one for sure overall. And uh, this one is little complicated. Okay, the del which we are getting from. So del from there. Acha. Okay, so what we are doing is that CML, as you can see this expression. Okay, this expression. Okay, so there we have replaced L is equals to this here, L equals to 8 lm. So if you do that, what you're getting here is that uh, L replace, so 1 by 4, 1 by 2 will come out, and lnm will be cancelled. So this will become 1 by 2 del I square. Okay, so the CML will become 1 by 2 del I square. Okay, and okay, the CML at L equals to this. Okay, it becomes 1 by 2 del I square, 1 by 2 del I. Okay, and 2 is there, so this expression comes. Okay, 2 and 1 by 2 and 2 will be cancelled, and we will get del I here. Okay, and so in what situation we are getting this? Okay, so CML and MTISI we are comparing. So this expression they have said is less than 0. Okay, and this one is 0. So to be less than 0, CMITISI should be greater than CML. Okay, okay, so this is the one. Okay, so that is the only way it can be less than 0, right? Simple. Okay, and TISI is less than L, so this is the only situation that can happen, so it should be D. Clear? Actually, not so much is required, just the inequality exploration. Actually, not a complicated problem, but complicated structure. Clear? Any doubt? Maybe the most complicated problem today. Any doubt? No doubts. Okay. But TISI is less than L. How do we conclude that one? Acha acha. So this is L here, and I proclaim that this is greater, and so it has to be greater. Okay, and it is any formula for C actually. This is the C formula, and if this CML in this situation TS is greater, and so TS has to be lower than L. Acha, correct. Okay, you understand this one. So this when we're putting L is equals to TS. Okay, this is greater than CML, general ML. Okay, so the TS which goes in the denominator should be less to make it bigger. Okay, so that is why TISI is less than L. Okay, understood? Understood? This is the UCB algorithm, UCB theorem. Okay, proof of UCB theorem. UCB algorithm and then the adjoining is UCB theorem. You have read, right? You have studied from the lectures. Quite complicated actually, to be honest. But UCB is a simple algorithm used in RL. Need to know that. The proof is not simple, but theorem is simple. Theorem states like this, that so these are the confidence bound, okay, or different actions, okay. So the first we are starting at the middle, then the estimate will take it up or little up or down, with some confidence also getting little up and down, okay. And we have to take the action with the maximum this, okay, means you have to take it on the top, okay, and and from the top, which is the maximum, okay. And so the process goes on and the bound gets smaller and smaller, so which led to taking a better estimate, okay. So the theorem is like that, UCB. Okay, few more questions left here, okay. uh, just let us just take 5 minute break, okay, and then we come again, okay, to solve these four problems, okay. Okay, okay, 5 minutes is just all I need. You can just see this one maybe. Okay, so welcome back. So everybody's here, I see. Nobody has left. Okay, so continuing. So what is true for the UCB algorithm? The action with the highest Q value is chosen at every iteration. So if I write it formally, the Q UCB algorithm. So there are K bandits, okay, K arms, okay, of the bandits, and so what you're doing is that we initialize. So initially, what we're doing, they're pulling each arm and seeing what reward we get, okay, and then we loop through um, pull any arm J that maximize. So we have to maximize this expression, okay, that is Qj. Uh, Qj plus under root 2 ln n. N is the number of discrete time of occurrence, okay. Suppose you have taken 100 samples, and nj here represents the number of time the action j has occurred. Suppose 10, okay. So so this is the situation, okay. So this is what we call the UCB algorithm, okay. And so what you're trying to do is that action with the highest Q value is chosen at every iteration, okay. So this is our Q value, okay. So this is the, so we're adding this is the actually our extra part, okay, in this, okay. This is the extra part, you can see. So that is what we are adding here, okay. And action with the highest Q value is chosen at every iteration. Do we take the highest one? This one is added here, okay, and highest Q value. Acha. So actually this is wrong, okay, because like Q value is this one exactly, okay, Qj, okay, but we're not taking the highest Q value. We are taking the highest Q value plus this, okay. This is taken, okay. So this one is wrong. Understood why? Okay, because we're not taking the maximum Q value here, but maximum Q plus this value, okay. Got it? After a very large number of iterations, the confidence interval of unselected action will not change much. So the action of confidence interval of unselected actions also change, because if unselected, this will not change, okay, this will remain fixed, but the number of iterations we are taking of the sampling will change, and this value will increase, okay. So the you see this one keeps increasing, so it is a underconfident estimation, okay. So the true expected value of an action always lies within its estimated confidence interval. Cha. Wait now. I think C is correct, right? Confidence of unselected actions will not change much. But after large number of iteration also they have told. So you have to see to that actually. So with the large number of iterations, unselected will not change. Large number of iterations, will not change too much. Can say so actually. Means like even if the n is already large, suppose 1 lakh, then 1 lakh 1 doesn't make much change actually. This may be correct actually. Let's see others. The true expected value of action always lies within its estimated confidence interval. Oh, this is not easy one. Okay. So anybody has done this problem? Again explain. Sure. You could have unmuted yourself, then I will explain again. Which one? NK? NK? Any doubt? Okay. Okay. So, but this question is a little more complicated. Uh, so B can be an answer. A is surely not an answer. Rest of the two options have to be seen. The true expected value of an action always lies within its estimated confidence interval. So the expected value of an action. Q's are the expected value of the reward of an action. Okay, not expected value of an action. Expected value of action का मतलब क्या है? Expected value of an action. Yeah, most probably no, because expected these Q's are the expected value of the reward of a function of an action. Okay, so most probably no, but soft no, not sure totally. With a small probability epsilon, we select a random action to ensure adequate exploration of the action space. Random action to ensure adequate exploration of the action space. Epsilon. Select a random action to ensure adequate exploration of the action space. Taking a small epsilon random action choosing. This is different. I think they are getting towards the that epsilon greedy approach for estimation of the QJ. Okay, but I don't think that is the point here. Okay, so this is surely wrong. Okay, I think B is the one, but C can also be true. Not totally sure actually, but I think B is the answer. Okay, here. Okay, any doubt? Maybe I'll clarify next time and come again at this question. Any doubt for now? Any doubt? No doubt. Okay. So let's move. So this is the question. Not a very difficult one. maybe difficult one. Let's see. This one is easy one. Okay, let me explain this one first. Okay. Uh, so four-armed bandit problem. 100 iterations of the UCB algorithms has already been done. Estimates of the Q values, 100 estimates, 100 after 100 steps the estimates are this of the Q value, and the number of times each of them are sampled are this. Okay, which will be arm will be sampled in the next trial. Okay, so how do we decide that? Uh, we decide by this. Okay, Q100 J plus under root 2 ln nj, not nj, n. Okay, so n here will be 100. Okay, so log of 100, but e base e is there. Okay, 2 is 2, nj is the values are given, n1, n2, n3, and these q values are also given. Okay, so you have to calculate 4 such expressions and the maximum will be sampled. Okay, so easy, actually you can do it right now. What will be the answer here? You can do the calculation. We can wait actually. Everyone, if you can do the calculations right now. Calculations you are doing or not? Anybody can reply. Problem is not hard. Okay, you have to calculate 4 expressions. Okay, you've got it already. Arm 2. Oh, very quick. Okay, and the values you got here, the 4 values, you have to use a calculator because the square root and log. I show you the values are. Acha. Okay, so you've got it right. So we have to put the values in the expression that I have written here and calculate. Okay, so the q values are given. Okay, and 2 is, well, 2 is a constant, you know. Ln log at the base e, this n is the 100 trials. Okay, so 100 will be n. Okay, nj are given, this is different, 25, 20, 30, 25. Okay, put these values, 4 values of this expression you'll get. Whichever will be the highest will be the answer. So the arm 2 should be the answer, as Aishwarya says, or maybe not. You know, whatever you get is the answer. Okay, Aishwarya must be must have done it, but like still you should check.
Sir, previous slide, sir.
Previous slide. Okay, this is the one.
Sir, how did you determine this arm 2, sir?
Arm 2, I did not. Aishwarya did actually. Yeah, Aishwarya. So who are you talking actually? Miss, I don't know.
No, sir, like on what basis does
Okay,
arm
okay.
tools?
So the basis is that this expression you have to, this will four expressions, you agree with that, right? Four expressions you have to calculate for every value of the j. Okay, there are four values of j, four arms. Okay, you agree or not?
Yes, sir.
Huh. So the one with the maximum value will be the chosen arm. So I think arm 2 should be the maximum. Ashwari has got it. The calculation is not too tough actually. Ashwari, you should be able to do it. Anybody's got anything? Okay, Himanshu already has
Yeah.
got the values. Okay, so you can compare. Okay, so arm 2 is the highest. Okay.
Okay, sir. Thank you.
Hmm. So maybe I should take a screenshot of this and put in the slide itself. Okay. So the confidence bound of each the UCB algorithm cannot increase with iteration. It can actually. So if you get to here, so if with each iteration, if the it is not selected, the nj remains constant, but n keeps increasing. Okay, so confidence bound can increase. Okay, so you can understand that. Okay, so the confidence, this represents the confidence bound. Okay, this expression, and so nj is constant if you are not selecting it, but n keeps increasing with every iteration, right? So it can increase if it is not selected, it will not remain constant. Okay, so the assertion is false. Okay, now nj terms in denominator ensures that the confidence remains the same for unselected arms and decrease for the selected arm. So that's also wrong. Okay, so both are wrong. Simple one, right? Not much calculation or dimagi. Any doubt?
No, sir.
No doubt, right? Okay. So our last question here from UCB, and that will be the last done. So what we are doing here is that we are replacing nj by nj square. Okay. So what it means that the it will quickly shorten the means reduce the, it will tighten the bound or reduce the confidence interval, leading to an quicker estimate. Okay, but what the problem is that you're exploring less. Okay, the same problem, we are exploring less but exploiting more. That is lead to uh, means errors in estimation. Okay, or you can get suboptimal arms, you can get, but may not also get. Okay, the process will be quicker but may get suboptimal arm. Okay, or may not get. Okay, as well, means like it can work out or it may go wrong as well, means, and the estimation will be more noisy, leading to uh, which can lead to suboptimal arms. Okay, uh, so the point is the suboptimal arm could be chosen less or more frequently depending on the samples. Okay, some optimal arms depending on the samples means how many samples you're taking. Okay, so if the samples is less, that is guaranteed to have suboptimal arm. If it is more samples, the after lot of samples, it will still converge to a good estimate. Okay, the point is that. Okay, but if it is like less samples, then it will surely be a wrong estimate. Mahalakshmi, you are joining so late, we are already done.
I'm sorry, sir. I have a poor network connection. That's why I'm unable to attend the class. It's okay, sir. I will
Okay, 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 no
see
problem.
the recorded session.
Yeah, recording sessions will be there. I will upload it today itself. You can watch there. Okay, for today we are done actually. Uh,
Okay, sir. Thank you.
okay, no problem. Any doubt in this one? this question you've got it? Okay. Any doubt?
So for this fourth option is the correct one, sir.
Fourth option is the correct one. It also depends on the sample. If the samples are more, it will still go to a nice convergence. Okay.
So if samples more, the suboptimal arms will be.
Uh, Means if the samples are more, suboptimal arms will be less. Okay. But if the samples are less, then suboptimal arms will be chosen more frequently. The point is that. Any doubt?
No, sir.
Okay. Okay, so we end it here. Okay, and we'll catch up on next week again on Sunday. Thank you very much. Okay, thank you. So the meeting ends now.
Thank you. Sir, do you have any other content for this RL, sir, for starting from the start?
What do you mean from the starting?
No, sir, we have, even though we have NPTEL lectures, do you have any other reference websites
The book
to
is the one to use. Okay, Barto and Sutton. It's
which
this
book, sir?
Barto and Sutton.
Can you spell it?
Okay, so this is the book actually, and you can see as well. But I think I'll put it in the chat. Online version available. Okay. Okay, so this is the classic book. Everyone uses this one. Balaraman sir supervisor also was Barto only. Okay, so we finish it here.
Sir, can you share the link, sir?
Can you?
Not selecting here. Can you share that link?
A link you can, if you just put it in the Google, you will get. The first option is the one to download.
No, sir, which you have shared, I could not copy it, so that I'm asking the link.
Acha, you are not able to copy. You have to write it down. Acha. Okay.
Uh,
Okay. I put the link only. So this is the one. Okay. Okay. Done. Done. You're done, Jocelyn.
yes, sir, done, sir. Thank you, sir. Thanks a lot.
Okay. Thank you very much, everyone.
Thank you, sir.